row operation can be represented by an elementary matrix. That means if we start with A and we get to the reduced row echelon form of A, we have the following expression in terms of A, the reduced row echelon form of A, and a product of elementary matrices. I've said it before and I'm just going to sum it up one more time, and that's that every elementary row operation can be represented as an elementary matrix. Another thing to note here before we check out our last example is that the order does matter. The first elementary row operation we do is represented by E1. The second elementary row operation we do would be represented by E2, and so on until the kth elementary row operation is represented by the elementary matrix EK. So let's take a look at an example of how we can utilize that last theorem. Essentially what we want to do first is we want to take our matrix A and we want to get it into reduced row echelon form by applying elementary row operations. And here's our reduced row echelon form. In the theorem, we often call the reduced row echelon form of A B. Now the reason that we apply these elementary row operations to get to reduced row echelon form is so that we have candidates for all of the E's that we need for the last theorem. So this first elementary row operation that we do, this is a candidate for E1. The second elementary row operation is a candidate for E2. And the third elementary row operation is going to be a candidate for E3. Take a few moments right now to pause the video and see if you can create the following three elementary matrices. Okay, so for the matrix E1, we'll end up with the following. For our second elementary matrix, we will multiply row 2 by -1/4. And for our third elementary matrix, we're going to take row 1 minus 2 row 2's. Note here that each elementary matrix, we have to start with a brand new identity matrix. This ensures that we do indeed have an elementary matrix, since we're only allowed to do one operation on an identity matrix in order to get an elementary matrix. Now we have all the building blocks we need to set up the equation. What we know from the theorem is that the reduced row echelon form of A is equal to a product of elementary matrices times the matrix A. Specifically, what we've done in our example is we've started with matrix A. We did 1, 2, 3 elementary row operations to get to the reduced row echelon form. Or, in other words, if we replace RREF of A with matrix B, we have the following. So, now it's just a matter of filling in all of the puzzle pieces. So, we know the reduced row echelon form of A looks like this. We've calculated all of our elementary matrices. We can put them here in the correct order. Now you have to be careful here, the order does matter. And we also know what matrix A looked like. So there it is. Now, if you're feeling particularly frisky, you could actually go ahead and do all of these multiplications over here on the right-hand side, and you should find that after you simplify everything, you get this matrix right here. The theorem is trying to tell us that if we take our matrix A, and we represent each elementary row operation as left-sided multiplication by an elementary matrix, after we do this multiplication, we should end up with the reduced row echelon form of the matrix A. Alright, my little epsilons, stay positive.